Last time you already learned about the attitude sensors. And then after we determine what our spacecraft attitude is, we need to know how to change it. Actuators provide torque and demand to rotate a spacecraft as needed to take pictures, downlink data, or meet other mission requirements. Typically, the two or more types of actuator combine to apply torque to achieve a desired attitude. There are two general classes of actuators which are active and passive. First, I will talk about the passive actuators. Gravity gradient attitude controls offers a simple, reliable, inexhaustible system as long as there is a gravity with no moving part. It controls only two axes, pitch and rolls. The gravitational force on the lower part is slightly greater than the force on the upper part, F1 more than F2. The same effect happened in more conventional shaped spacecraft due to the difference in internal mass distribution. The structure of gravity gradient boom consists of a base which is attached to the satellite. This base unit contains a deployment system which, once the satellite is in space, deploy the boom structure which holds the tip mass. The boom can either be a rigid structure like a truss or it can be made out of wire. Boom length vary from hundred of centimeters to hundred of meters depending on the orbit, mass of the satellite, and mass of the wake at the end of the boom. The mass at the tip of the boom is the last major piece to this system. This mass can vary, but is generally only a small percentage of the satellite total mass, approximately 5 to 10%. The gravity gradient boom is sent into space as part of the overall satellite structure. As the satellite is deployed from the launch vehicle, the force of gravity acts on the gravity gradient boom and the satellite equally because the boom is stowed inside the satellite during takeoff. A damper is another actuator that usually used in combination with others for a complete system. A damper is a device that changes angular momentum by absorbing the energy. The spin-stabilized spacecraft takes advantage of the conservation of angular momentum to maintain a constant initial orientation of one of its axes. Because the angular momentum vector h of a spinning mass is fixed in inertial space, the spacecraft tend to stay the same inertial attitude. Spin stabilization is useful as long as we want our spacecraft to stay pointed in the same inertial direction. However, usually we are more interested in non-inertial pointing. For example, spin stabilization is not very useful for a pointing h at Earth. One way to avoid Earth pointing limitation of spin stabilization is to use dual spin system. Dual spin system take advantage of the constant angular momentum vector of a spinning mass. This system consists of an inner cylinder called the disband section, surrounded by outer cylinder that is spinning at high rate. The outer cylinder provides overall spacecraft stability. To allow for antenna and sensor pointing the disband section at a rate to keep them pointed at Earth. For example, if a spacecraft is in geo orbit, the disband section rotates at orbit rate or once every 24 hours, keeping antenna or other sensor focused on Earth. The example of the dual spin system is our MESAT-1 satellite.